Exact match marks valid SQL as wrong when two queries return the same rows. DuckDB execution accuracy compares result sets instead, so your evaluator stops rejecting correct answers. You'll learn how the pieces fit into a workflow that executes generated and reference queries and scores matches by returned rows. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Text-to-SQL systems often get judged by string equality of SQL text. That fails in practice because many different queries can return the exact same answer. Execution accuracy evaluation flips the lens. Instead of matching text, we run both queries on the same database and compare the results they return. Practitioners reach for this when they want fairer, more robust metrics for model development and prompt tuning. The intuitive idea is simple. Give the predicted SQL and the reference SQL the same stable database. Execute both. Compare the returned rows. If the rows match under a clear policy for order, nulls, and small numeric drift, count it as correct. For example, a grouped sum that appears in two different orders should still pass. The strengths are fairness and simplicity. The weakness is you must control the database state and agree on tolerance rules. We will build a small, repeatable DuckDB-based evaluator that runs pairs of SQL, normalizes results, and reports an execution accuracy score. That keeps the code compact and the policy explicit, so you can iterate quickly on prompts and models. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves different. To start, we need a tiny in-memory database that never changes between runs, so comparisons are stable. This snippet creates a tiny in-memory DuckDB fixture you can reuse for repeatable text-to-SQL checks. The first thing your evaluator needs is a stable database state, not a moving target from a shared warehouse. DuckDB.connect gives us a local connection. Con.execute creates the schema, and con.execute many loads 3 visually readable rows. The table includes a none value, so later snippets can handle SQL null behavior instead of pretending every answer is clean. The visible output confirms the fixture row count, which matters because every later comparison depends on this exact data. Having a fixture means we can test ordering differences next, because models often change order by without changing results. This example compares two DuckDB queries that return the same grouped result in different orders. Exact string matching would reject pred SQL, even though adding order by city desk does not change the aggregated answer set. The code executes both SQL strings with con.execute.fetchall, then sorts the returned Python rows before comparing them. That makes row order an evaluator policy instead of an accidental failure mode. The visible output shows the order-safe comparison passes, which matters because many text-to-SQL models produce harmless ordering differences. Now imagine an aggregate that produces a null. We need a stable way to compare nulls across execution and serialization. This code adds a DuckDB row that forces an aggregate result to contain null. Nulls are easy to mishandle when results are serialized, logged, or compared across runs. So clean converts Python none into a stable marker before comparison. Ref SQL names the grouping column directly, while pred SQL uses group by one, which is structurally different but execution equivalent here. Both queries still run through con.execute.fetchall, so the evaluator is judging return data rather than query shape. The visible output shows one normalized null cell and a passing comparison, which matters for avoiding false failures in sparse result sets. Scalar values can be noisy, so we should allow tiny numeric differences instead of demanding bit-for-bit equality. This snippet checks a scalar DuckDB result with a numeric tolerance instead of exact equality. Small numeric differences can appear when generated SQL uses a different expression, cast, or rounding path. So the evaluator should decide how much drift is acceptable. Base SQL keeps the shared revenue calculation visible, while PredSQL deliberately adds a 1 cent difference. The code fetches both scalar values with con.execute.fetch1, computes delta, and compares it to 0.05. A larger tolerance accepts more near misses, but can hide meaningful mistakes. A smaller tolerance is stricter, but may reject acceptable numeric variance. The visible output shows the delta and whether it is inside policy. With those pieces in place, we can make a tiny evaluation loop that runs many pairs and reports a single execution accuracy number. This example turns the earlier DuckDB checks into a tiny execution accuracy baseline. The pairs list represents reference SQL and predicted SQL from a prompt or model run. Norm executes each query with con.execute.fetchall, normalizes nulls through cell, rounds floating point values to 2 decimals, and sorts rows before comparison. That gives one consistent policy for row order, null representation, and small numeric differences. This is still a compact teaching baseline, but the same shape can be logged per experiment run. The visible output shows how many SQL pairs passed, and the final execution accuracy, which is the score you can track across prompts or models. This tiny fixture maps easily into a larger experiment. Replace the small pairs list with outputs from your model, and persist the per pair pass flag to track where failures concentrate. 3 quick points to remember. Execution accuracy evaluates returned rows, not SQL text. Use it when you want fair scoring across logically equivalent queries. One caveat is that it depends on a stable, well-defined database state and clear policies for order, nulls, and numeric tolerance. A useful next step is to log per example diffs and tune the numeric tolerance on a real dataset like the Spider Deb set. Then track how changing tolerance affects your execution accuracy per prompt variant. If practical AI engineering helps, subscribe and watch the AI engineering videos.